Neural networks are not particularly new. We've seen that precursors such as the perceptron date back to the 1950s, and although disappointments relating to the perceptron led to some setbacks in the late 60s and 1970s, by the 1980s neural network research was back in business. Most of the elements of neural network machine learning models that we know and love today were all in place in the 1980s. Backpropagation, as we know it, was published in 1986. Convolutional neural networks were applied to the handwriting recognition problem in 1989, and other precursors to CNNs date back to at least the beginning of that decade. And yet, to a significant extent, neural networks went out of fashion a bit with the rise of SVMs and random forests, and it wasn't until the advent of deep learning in the 21st century that things got back on track. One of the reasons for this was that as researchers in the 1980s and 90s attempted to scale up their neural networks to tackle bigger, more complicated problems, they started encountering difficulties getting the models to converge. There were a number of different reasons behind this, but two significant ones were to do with activation functions and initialization. So we've introduced activation functions as a source of non-linearity to enable the network to combine its different linear pieces into bigger, more complicated boundaries or regression landscapes. In the early days, the most popular choice of activation function was the familiar sigmoid or logistic function that we've seen before for logistic regression. This was thought to be interesting for the same reasons we used it in logistic regression, because it was a smooth approximation for the hard threshold boundary. However, it has a couple of problems when used as an activation function. In particular, it is asymmetric, so its values are all positive. So there's never any negative outputs from the individual neurons. Another problem that it has is that it has very flat gradients for much of its support. So it's only the narrow range between, say, -2 and 2 that has any significant output value, and the rest of the time its outputs are pretty much 0 or 1, and the gradients are extremely flat. So this makes it difficult to train. An alternative activation function that was introduced a bit later solved the asymmetry problem for the sigmoid, and this is the hyperbolic tangent or tanh function, which looks like this. This has slightly better properties in that it can support outputs that are negative as well as positive, but it still has very flat gradients away from 0. One of the great innovations in the early 21st century, significantly appearing in the AlexNet deep network that triumphed at the ImageNet large-scale visual recognition challenge, sort of ushering in the age of deep learning, was the use of the ReLU or Rectified linear unit activation in place of the sigmoid or hyperbolic tangent. ReLU has a much simpler form. It thresholds at 0, and anything above is just left as it is. It does not suffer from vanishing gradients, at least for the positive cases. It is still asymmetric, but that's not as big a problem. ReLU does suffer a bit because it has a completely flat output for any inputs that are less than 0. It just flattens them to 0 and it has no gradient at all. However, in practice, ReLU works a lot better and is still probably the recommended activation function for most purposes today. Some variations on ReLU have been developed to attempt to get around this flat gradient below 0. For example, the leaky ReLU has a much smaller gradient below 0 but is not completely flat. And the ELU, or exponential linear unit, has a smoothly changing value that asymptotes to something a bit below 0. In practice, there is not much evidence that these achieve a great improvement in convergence over simple ReLU. The big issue with vanishing gradients and the zero gradient for negative inputs to ReLU come down to a downside of backpropagation, or the chain rule, which is that it involves doing a lot of multiplications. Multiplications are nice and straightforward, but they suffer from a couple of problems. Firstly, zeros are lethal. A zero anywhere in your chain of gradients will kill the propagation completely, and no more information will flow backwards. So there will be no learning in any of the neurons that lead up to a zero gradient. More generally, if there are a lot of small numbers in your product, then the output will tend to be very small. If there are a lot of large numbers in your product, then the output will tend to explode to be very large. So activation functions that introduce these kind of numbers into the chain of gradients can make it very difficult to train. For functions with ReLU activation, this can lead to a problem known as dead neurons. If the neuron never fires for any of the inputs in the training set, then it will never learn anything. Nothing will change, and it will just remain as it is forever. When training a neural net with any gradient descent-based method, it's necessary to start somewhere. These are iterative methods that proceed from an initial point and hopefully move towards the global, or at least a good local minimum. With the single lone perceptron, we were able to get away with just initializing the weights vector to 0. However, when we're dealing with multiple neurons, we can't do that. We need in some way for them to be initialized with different weights. Otherwise, as the back propagation proceeds, all of them will have the same gradients and they will all learn the same things, which rather defeats the purpose of having an ensemble in the first place. So traditionally, the done thing is to initialize the weights randomly, providing a population of different values that the learning process can draw from. Traditionally, this was done in a rather ad hoc fashion, drawing on some random distribution, usually over a smallish uniform interval, or else from some Gaussian with a small standard deviation. However, it turns out that the variance of the initial weights, the range that they cover, is actually really important for the trainability of the network. We want to maintain a varied and active population of different neurons throughout the network, throughout the training, both so that the forward pass produces useful outputs and also so that the back propagation pass produces useful gradients to learn from. If the variance of the initial weights is too high, then this can lead to the linear sums exploding, and that in turn can lead to the activations saturating and the gradients going flat. If the variance is too low, then you can equally wind up with the activations going to nothing and there being very little variation in the population. In either of these cases, you can wind up with an untrainable network. It turns out that the optimal variance for initialization weights depends on the number of neurons in the particular layer that you're initializing. Based on analyses from the last decade or so, a couple of different initialization schemes have been developed that optimize the weights variance for the initial weights according to what the activation function is. It turns out that because of the asymmetry in the ReLU activation function, it has a somewhat different optimal initialization variance from a symmetric activation function like the hyperbolic tangent. There are two common initialization schemes that are used, one for each of the kinds of activation function. The Glorot or Javier initialization is typically used for hyperbolic tangent activations, and it looks like this. It comes in two forms, whether initializing a uniform interval or initializing with a normal distribution. Alternatively, for the ReLU activation function, the preferred initialization is the Kaiming-He initialization, which looks like this. Again, you can choose to use a uniform distribution or a normal distribution in order to do the weights initialization. Fundamentally, there's not a huge difference between these two initializations, but the he initialization gives a slightly higher variance to account for the fact that the ReLU activation function will eliminate a whole chunk of the outputs, those that are below 0. Initialization is primarily important at scale. It doesn't matter so much for small, shallow networks with not very many neurons. But the effect of multiplying up the gradients during backpropagation really increases with the depth of the network. This is one of the reasons why shallow networks successfully trained in the early years of the 1980s and 1990s, but it became harder as the networks got deeper. Rounding up then from our first week of discussing neural networks, what have we learned? Well, first of all, neural networks are great. They're really capable, they're really versatile. They can learn arbitrarily complex decision functions or regression landscapes. They tend to be very black box, implicit, and essentially uninterpretable, although we'll come back a bit to the question of interpretation in a couple of weeks. They require care in order to train. It's quite easy with a bad initialization or a bad choice of activation function to wind up with a network which fails to converge. They've been around for a long time, and most of the machinery involved has been around for at least 30 years, but they've had a recent renaissance as a result of, let's say, 3 factors. The first is just increased computational power, especially in GPUs. The second is increased data availability, especially as a result of the explosion of the internet. Finally, there are subtleties in the training and developments of algorithmic variations so that things like initialization and activation work better and the networks become easier to train. So far we've just scratched the surface, and we'll be talking about neural networks more in the next session after Reading Week.